Hello everyone, welcome back to the channel Code with AKJ. Today is day 55 of our LeetCode and 5 challenge, and today we are going to solve another problem from binary search module, which is find peak element. So before we begin, make sure to like, share, comment and subscribe to the channel for daily coding videos, explanations and latest updates. So let's get started with our problem statement. So the problem statement says a peak element is an element that is strictly greater than its neighbors. Given a zero indexed integer array nums, find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. You may imagine that nums of -1 and nums of n is minus infinity. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. You must write an algorithm that runs in O of log n time. So we are given an array nums and we need to find any one peak element. So a peak element is strictly greater than its neighbor, that is greater than its left element and the right element. And we also assume that nums of -1 and nums of n should be infinity, which means edges can also be peaks, which is first element can also be a peak element and last element can also be a peak element. And the important constraint here given in our problem statement is that we must solve this problem in O of log n time complexity. So this is all about our purpose statement. So let's go through these two given examples to understand. So we are given nums array 1, 2, 3, 1, and we can see that 3 is our peak element as it is greater than its left neighbor and right neighbor. So we'll return its index value, which is 2. Coming to the second example, we have given nums array 1, 2, 1, 3, 5, 6, 4, and we can see that 6 is the peak element which is greater than its left neighbor and right neighbor. So we'll return its index, which is 5. So let's get started with our brute force approach. So from the given examples, we can observe that the peak element is the greatest element inside our array. So in this given array, the greatest element is 3. So we'll return the index of this greatest element, which is 2. So coming to the second example, the greatest element of this given array is 6, and we need to return the index of this greatest element, which is 5. The straightforward approach here would be to find the greatest element of our array and we return the index of that greatest element. So the time complexity of this approach would be O of n, as we are iterating over our array to find the maximum element, and the space complexity of this approach would be O of 1, as we are not using any extra space to store any values. So let's quickly go through the code and let's submit. So here's the code for our first approach where we are finding the maximum element and returning the index of our maximum element. So here I've taken the maxi variable, which would be initially int min, and our index variable, which would be initially 0. So we'll run a loop and we'll compare each and every element with our maximum variable. So whenever we find a next greater element, we'll update our maximum variable with that particular element and we'll store the index of that element. And finally, after finishing our for loop, we'll get our maximum variable and the index of our maximum element. So we'll return that index variable. So let's quickly run this code. Yeah, it's working. So let's submit. As you can see, this gives us successful submission, but according to our problem statement, the time complexity of our solution should be O of log n, not O of n. So let's try to optimize our approach and let's try to use binary search in this problem statement. So to use binary search, one of the conditions should satisfy, that is, it should be in sorted order. So here, as we can see that the array is not sorted, but there's still a property which helps us to use binary search in this problem statement, that is using slopes. So let's try to draw a graph based on these values. So the value 1 would be here, 2 would be here, 3 would be placed here, and then 1 again would be pointing here. When we try to draw a line along these points, so we see a slope which is going upwards, and then we'll find a peak point, and then the slope goes downwards. So in this way, we'll try to use this slope property which is going up and down, and we'll compare elements with each other to find whether the slope is going up or down, and based on these slopes, we'll find whether we have reached the peak point or not. So the left part of the peak point is also considered as a sorted part, and the right part of the peak point is also considered as a sorted part. So we use this particular idea to find our peak point, and in this way binary search helps us to find our peak point in O of log n time complexity. So we'll use this particular idea to find our peak point. So we'll have two conditions. So if the nums of mid is less than nums of mid plus 1, it means the slope is going upwards. So the peak element must lie on the right side. So we'll move our low pointer towards right by mid plus 1. Another case here would be that if nums of mid is greater than nums of mid plus 1, then it means we are on a downward slope, and which means the peak element must be on the left side. So we'll move our right pointer to mid minus 1. So in this way, this slope behavior guarantees a peak exists in the direction of the higher slope. So with the help of this slope ideology, we'll find our peak element and we'll move our pointers accordingly based on these two conditions. And why binary search works here? Because of the slope behavior, which generally shrinks our search space half by each time. So let's do a quick dry run on these two examples and then we'll code our approach. So here's a quick dry run on our first example 1, 2, 3, 1. So we'll start our algorithm by initializing two pointers low and high. Low would be 0 and high would be array size minus 1, which is 4 minus 1, 3. And the first step in our binary search algorithm here would be to find mid pointer, and we'll find it with the help of the formula low plus high minus low by 2. So in our first iteration, the low would be 0 and the high would be 3. So our mid pointer gives us value 1. So we'll check two conditions, whether the nums of mid is less than nums of mid plus 1 or nums of mid is greater than nums of mid plus 1. So why we are checking these two conditions? To know whether the slope is going upwards or downwards. So based on the slope's behavior, we'll try to shrink our search space and we'll move our low and high pointers accordingly to find our peak element. So here we'll first check whether the nums of mid is less than nums of mid plus 1, which is nums of 1 is less than nums of 1 plus 1, which is 2. So nums of 1 is 2 and nums of 2 is 3. So since 2 is less than 3, it satisfies the condition, which means the slope is moving upwards. So we'll move our low pointer to mid plus 1. So mid is 1 and low is 0, so our low pointer would be pointing to index 1. So our low pointer is pointing to 2 and our high pointer is pointing to 1. So coming to the second iteration, we'll again find our mid pointer with the help of this formula. Now the mid pointer is 2. So again we'll check two conditions, is less than mid plus 1 or is greater than mid plus 1. So nums of 2 is 3 and nums of 3 is 1. So since 3 is greater than 1, so it does not satisfy this condition. Check the next condition, which is whether it is greater than nums of mid plus 1. Yes, 3 is greater than 1, so it satisfies the condition, which means slope behavior is moving downwards. So in this case, our high pointer would be pointing to mid, ensuring that mid can be our possible result. So right now, since mid is pointing to 2, the high pointer would be pointing to mid value, which is 2. And low pointer is still pointing to index 1. So we'll move on to the next iteration. Right now, the low pointer is pointing to index 1 and high pointer is pointing to index 2. So again, we'll find our mid value. So this time it gives value 1. So we'll again check these two conditions, whether we are in the upward direction of slope or downward direction of the slope. So we can see that we are in the upward direction of the slope. So we'll move our low pointer forward, which is mid plus 1. So low pointer would be pointing to index value 2 and the high pointer would be pointing to index value 2. So whenever we find a case where the low pointer is equals to high pointer, we'll break from that loop. Or else if we try to continue in this condition, we will be stuck in a infinite loop and we'll never find our peak element. So this would be our break condition when low pointer is equals to the high pointer. And we'll break from the loop and we'll return either low pointer or high pointer, which would be pointing to our peak element. So in this case, our peak element would be index 2, which has a value 3. So 3 would be our answer for this given example. So in this way, binary search helps us to find our peak element in O of log n time complexity. And coming to the space complexity here, it would be constant as we are not using any external data structure to store any values. So this is how binary search works in this problem statement to find our peak element. So let's quickly code this approach and let's submit. So here's the code for our optimal approach. So we'll start our code by initializing two pointers, start and end. So here I've taken start and end, which would be initially 0 and n minus 1. We'll initially find our mid pointer, which would be start plus n minus start by 2. So we'll run a loop until or unless start is less than end, and we'll check these conditions. If nums of mid is less than nums of mid plus 1, it means the slope is moving upwards, and we'll move our start pointer to mid plus 1. Or else we are in the downward direction of the slope, we will move our right pointer towards the mid, ensuring that mid can also be a possible answer. And for every iteration, we'll again find our mid pointer for the next iteration. So after finishing our loop, our both pointers would be pointing to our peak element, so we can either return start or end. So the time complexity of this approach would be O of log n, and the space complexity here would be constant. So let's quickly run this code. It's working, so let's submit. As you can see, this approach also gives us successful submission, but this time our time complexity is O of log n, which is been suggested in our problem statement to use. And that's it for day 55 of LeetCode 75 challenge. We learned what peak element means, and we have used brute force approach, which takes O of n time complexity. And then we have optimized using binary search algorithm, which has O of log n time complexity. And we have also seen why slope direction helps us using binary search algorithm. And we have did a complete dry run on our first example, and finally coded our approach. So if you enjoyed this explanation, please like, share, comment, and subscribe for daily coding solutions and updates. Till then, keep coding, keep growing. Thank you.